Hello viewers, in this program we are going to take up a very important topic related to network security. It is about virtual private networks, or in short termed as VPNs. A VPN is a protected network session formed across an unprotected channel such as the internet. A VPN allows an outside user to participate on the internal network as if connected directly to it. Many organizations have a false sense of security regarding their remote access just because they have a VPN. However, if an attacker compromises the machine of a legitimate user, a VPN can give that attacker an encrypted channel into your network. You might trust the security of your perimeter, but you have little control over your telecommuter systems connecting from home, a hotel room, or an internet cafe. Similar issues of trust and control arise with the security of nodes connected over a VPN from your business partner's network. Let us start with the basics of VPN. A VPN is a connection that is established over an existing public or shared infrastructure using encryption or authentication technologies to secure its information. This creates a virtual segment between any two entities that have access. This might occur across the shared infrastructure of a local area network, WAN connection, or the internet. In this program, we will focus predominantly on VPNs that traverse the internet as a means to create a secure channel over its public infrastructure. Such channels make for an inexpensive and effective remote networking solution that anyone with internet access can take advantage of. VPNs can be categorized into three basic configuration types. These are host to host, host to gateway, and gateway to gateway. Regardless of which media the VPN uses, which type of configuration it represents, or what shared infrastructure it crosses, the VPN is a powerful tool that can be used in many different ways to create a secure communication channel. Let us learn about basics of VPN methodology. The basic concept behind a VPN is securing a communication channel with encryption. Communication can be safeguarded through encryption at many different layers of the network, such as application layer, transport layer, network layer, and data link layer. At the application layer, encryption can be applied with programs such as Pretty Good Privacy, that is PGP, or through channels such as Secure Shell, commonly known as SSH. In addition, remote signal session programs such as PC Anywhere and multi-session programs such as Terminal Server can be used with encryption to protect remote communication. At the transport layer, protocols such as Secure Socket Layer, commonly known as SSL, can be used to protect the contents of a specific communication between two parties. This is typically used via web browser communications. As with application layer protection, the contents of the communication are protected, but the IP packets that carry this information are available for inspection. SSL can also be used as a tunneling facilitator for other communication session types using a product called Stunnel. At the network layer, protocols such as IPsec not only encrypt the payload of the packet, but they also encrypt TCP/IP information. Although the IP address information for the parties that are encrypting and decrypting the packet is necessary to facilitate proper routing, higher level information including transport protocol and associated ports can be completely hidden. Endpoint station IP address information can also be hidden if a gateway device such as a router, firewall, or concentrator is doing the encryption using a concept called tunneling. Let us first understand what is tunneling. Tunneling is a process of encapsulating one type of packet inside another to facilitate some sort of transport advantage. For example, tunneling could be used to send broadcast traffic across a routed environment or to secure IP packets with encryption. One effective demonstration of tunneling as a means of encryption can be illustrated by using a gateway-to-gateway VPN example. The two networks in the figure shown on the screen are interconnected via a VPN that is terminated at either end by a firewall. The firewall in this example translates any packet that is destined for the remote network into encrypted form, and it adds a new IP header to the resultant payload with its own IP address as the source address and the remote firewall address as the destination IP address of the packet. Encryption hides the actual IP information of the original packet. When the remote firewall receives the packet, it decrypts the packet back to its original form and passes it to the host for which it was originally intended. The virtual segment being created between the two gateway endpoints is called a tunnel. The hosts have no knowledge of the fact that the packets are being encrypted or that they are being sent over a public network. No special software or configuration is required for the hosts. When a host sends a packet that is destined for a host on the remote subnet, the VPN process is handled completely by the gateway devices. When tunneling is used, even though host system IP addresses are masked from the outside world, they don't have complete anonymity because the IP addresses of the gateway devices are available. The eavesdropper can still determine who is communicating with whom. Maybe this won't give away communication streams on a host-to-host level, but it might on a network-to-network level, which could tell an outsider a lot. For example, what if it is rumored that Mr. X is a spy for Switzerland? The government immediately starts to monitor his internet connection and determines that he is using a VPN. We can't tell what his communications are about. However, if we know Mr. X owns the source address and the destination is somewhere in the Switzerland, we might want to investigate further. Now let us know something about VPN protocols. First to be discussed is IPsec. IPsec's goal is to facilitate the confidentiality, integrity, and authentication of information communicated using IP. This is accomplished through the use of several protocols, including Internet Key Exchange, that is IKE, encapsulating security payload, that is ESP, and authentication header, that is AH. These three protocols combine to allow the secure exchange of information without fear of outside eavesdropping or tampering. A second goal of the security suite is a means for multiple vendors to have a set of standards by which they can interoperate securely. IPsec based security starts with forming of a security association between two communicating parties. A security association termed as SA is basically an agreement between two entities on how they will securely transmit information. One of the exceptional things about IPsec is the openness of its standards to support not only multiple protocols and communication modes, but also various encryption algorithms and hash types. All these details must be pre-negotiated before the secure exchange of user data can begin. The resultant agreement is an SA, that is security association. Each communication session has two SAs, one for each communication partner. Each partner negotiates a new SA for every IPsec connection he makes. Before a security association is negotiated, the particular settings that an IPsec partner is going to support must be configured for it locally. These settings are held in what is known as Security Policy Database, in short termed as SPD. After the security association has been negotiated, it is contained in a security association database, that is SAD. This is necessary because different communication rules can be configured for each of the session that a host or device might initiate. Because multiple IPsec sessions are available per device, each with its own set of unique settings, for this process to function correctly, each SA session must have its own singular identifier. This identifier is made up of a unique security parameter index that tells which SA database entry pertains to the connection in question, the destination address of the connection, and the protocol identifier for the ESP or AH protocol, whichever is being used for the connection. An IPsec connection has two basic modes, transport and tunnel. Transport mode is a host-to-host form of communication and involves the encryption of a packet's payload only. Because of this host-to-host requirement, software needs to be loaded on all communicating hosts, which in large installation can be a big problem. However, this VPN mode is well suited for encrypted communication between hosts on same network, or in situations where it is important to be able to differentiate hosts by their IP address information. Transport mode lacks a means to do gateway-to-gateway communication and the ability to conceal host IP information, which can be a major concern when your data is traversing a public medium such as the internet. The other IPsec mode takes advantage of tunneling. Tunneling mode is the method of choice for most VPNs because it encrypts not only the payload but also the entire original packet, partially or completely the source and destination addresses of the communicating systems. Most VPNs use tunnel mode and have at least one gateway device. There are many other VPN protocols like PPTP, L2TP, etc. So viewers, now you must be having an idea about benefits of using virtual private networks. The main benefit of using a VPN for remote network access can be termed as the price effectiveness of being able to utilize a public medium to transport private information as securely as possible. A VPN can supply many levels of security to a shared network medium, including improved confidentiality, integrity, and authentication. Because a VPN utilizes existing infrastructures, it can be implemented swiftly without having to wait for the establishment of a line or other factors that commonly hold up such implementations. The combination of security, quick setup, and cost effectiveness can make a VPN an excellent communication solution. VPNs offer many security features that make them a powerful method for securing information traveling across insecure territory. These features can be customized depending on the hostility level or insecurity level of the environment. This security level must be balanced against the value of the data. Regardless of the strength of the chosen encryption technology used for VPN, Your VPN should still offer the requirements of a secure communication channel. The three requirements, namely confidentiality, data integrity, and authentication, are the most basic. Confidentiality is the guarantee that no one else is going to be able to peek at your information. The encryption algorithm that scramble your private data into meaningless segments of characters provide this for a VPN. Data integrity is the next issue that can be protected through encryption and VPN use. Integrity verifies that the information you are receiving is the same as it was when it was sent to you. Authentication verifies that the information has come from whom it is supposed to, and in turn that it is received by whom is supposed to receive it. VPN provides deployment advantages as it can be deployed on the existing infrastructure with little modifications. The infrastructure available at one place can be made available at a remote location in a secure way. A VPN can save money in many ways, most of which involve the VPN replacing some type of high-cost dedicated WAN link. Despite all their positive points, VPNs have disadvantages too. You must consider the disadvantages before confirming that a VPN is suitable for your environment. The use of encryption brings about an additional processing burden, most likely to be handled by your existing gateway devices or by additional equipment that must be purchased. Fitting a VPN into an existing location can also be a challenge in some environments due to the additional packet overhead. A VPN has significant design issues that novices will most likely not want to tackle on their own, and the troubleshooting traffic that is encapsulated can be a real challenge for even the most experienced practitioners. Processing overhead encryption, the backbone of the VPN, involves incredibly complex mathematical computations. These must occur for every packet that is sent across and received by a VPN gateway device. These complicated computations take their toll not only on the gateway device but also on the overall bandwidth of the VPN connection. This speed reduction intensifies with stronger encryption algorithms, which in turn require more mathematical complexity and more processing bandwidth. This problem has become such an issue over time that special offload cards have been created to help absorb some of the additional processing burden of VPN encryption. These hardware acceleration devices can improve the detriment of lost processing power but a hefty price. In turn, it is important to make this processing burden a part of your hardware and bandwidth determination requirements when deciding on a VPN. Packet overhead. Another interesting disadvantage of implementing a VPN is the additional overhead that is added to every packet. Existing packets can be encapsulated, which require the wrapping of a original packet in additional packet overhead. Even if you aren't using encapsulation, additional header information still adds to the packet size. In either case, this overhead, although not substantial, can be enough to become a design concern in some environments. In addition, adding size to every packet can negatively affect network bandwidth, not only due to sending larger packets but also because each larger packet is more likely to need fragmentation as it journeys across various gateways and routers. This fragmentation will negatively affect network performance. Implementation is a concern when making a VPN part of your existing network infrastructure. Some of these implementation issues include incompatibility with network address translation, that is NAT, VPN pass-through usage, and maximum transmission unit size and design issues. So, dear viewers, today we have discussed the basics behind how VPNs work and process of tunneling. We discussed the advantages of VPNs, including security, deployment, and cost benefits. We also looked at some disadvantages too. So, wish you very happy learning. Thank you.